All right, good morning everybody. It's 9 o'clock. We're missing just a couple people here, so I'm not sure if Blackboard Collaborate is giving some issues this morning to some people or what, but hopefully they find their way in. Just a couple of announcements, actually technically only really one announcement before we start Unit 3. And that is that I'm sure you're well aware of it and you've heard it in all your classes before, but the end of quarter 1 is coming up really quickly. So November 6th, technically I think is the end of quarter 1, but November 5th is that Sunday deadline right before it. So all quarter 1 work is going to be, needs to be handed in by that November 5th deadline. And like I said, November 5th is a Sunday, so it kind of does follow your normal deadline procedures there. You have until midnight on the 5th to get everything in. The only thing different this time around now is after that deadline passes, any zeros that are in the grade book for missing work will turn permanent at that time for quarter 1. So after November 5th, we are solely focusing on the second half of the semester. And you guys have been through it all, so you're already aware of that and know what needs to get done. Now, I highly suggest taking a look at your grade book this week and planning accordingly on how you're going to get those missing assignments turned in. If you need my help creating a pacing chart or whatever it may be, please email me to let me know. So I'm here to help you. So even if you're behind, I'm here to help you succeed. I want you to succeed. So if you need my assistance in getting there, please let me know. Okay, with that being said, are there any questions regarding that November 5th deadline for quarter 1? Or are there any questions in regards to Unit 2 at all? Because today technically we are starting Unit 3. Yes, you are. So the Unit 2 test, I know it encompassed a lot of information with your higher degree polynomials. If you need to make corrections on that test, you most certainly can for half your points back. Just remember to show your work on how to get that correct answer. But most definitely you can make corrections. If you need to make corrections with me because you can't figure out how to get the correct answers, make sure you sign up for office hours. I've been adding extra office hours every day just about. So take a look at the calendar. You might have to scroll a little bit to see those extra hours I'm adding, but I am adding extra spaces. So if you need to, you can come to me and I can help you through that as well. Yeah, so it should be in the Unit 2 module. So go to modules. I think it should be Unit 2. I believe there was a practice test and then an actual test. I want to say it might have even been called like test form A or something. I can get in there and look just a sec. So in the modules area, we're working in Unit 2. It's the very last thing in there, and it just says Unit 2 test. If you haven't taken your test yet, because it was due at the end of last week, so some people maybe were studying a little bit more and plan on doing it early this week. If you haven't taken your test yet, just note that you can use a graphing calculator and your notes when you're working through that. Any other questions regarding Unit 2 at all? For the most part, the test went okay. We're looking at like a low B, mid B average on it. So for the most part, it went okay. Unit 3, we're continuing moving forward. We're focusing on exponential and logistic functions. This is the last unit before we hit trigonometry. So before we start seeing our sine, cosine, and tangent, take in and soak in all the algebra that you can, because we'll be spending probably until Christmas time, maybe even into the new year, looking at trigonometric functions. So working a lot with our sine, cosine, and tangent stuff. So if you enjoy the algebra side of things, soak it in for one more unit here, because we'll take kind of we won't really take a break from it, but we'll switch gears a tad bit in Unit 4. All right, so the good news is most of the stuff, I shouldn't say most of it, about half of the material we're going to look at in Unit 3 is going to be review, and then obviously we're going to add some new stuff to what we already know. So we have looked at exponential and logistic functions in Algebra 2. Exponential, we're going to start with actually talking about what is an exponential function. So as a recap here, an exponential function takes on the form of y equals some constant, and usually you multiply that by some number to a variable. Now the biggest thing to note with your exponential function is that you must have a variable in the exponent. So that kind of goes hand in hand with the title of the name, right? Exponential. You're expecting something to happen in the exponent of the area there, so the area of the exponent, right? So exponential function means you must have a variable in your exponent somewhere. And we'll talk about the different types of exponential functions that we're going to be facing coming up here in a little bit later in class. Now please note that b is what we call the base of your function, right? A is going to be some constant, and it can't be 0. So a can be any value out there except for 0, because what happens if a was 0? What would be the problem if a equaled 0 in our function here? It wipes everything out, right? If a is 0, technically you just get a horizontal line through your x-axis at y equals 0. That's not exponential, so we do have one small restriction, and that is that that constant out front cannot equal 0. So anything else is fine except for a being 0. Your exponent can also take on any value. So positive, negative, fractions, anything like that is going to be okay as long as there's a variable with it up in the exponent. A, so we said that a cannot be 0. A is also your initial value. That comes into play with story problems. So when you're looking at what the starting value of your function is going to be, the starting point, that is going to be the a value of your function. B is what it's increasing or decreasing by. So B is what we call that base. It's what you multiply by to get to the next term in the sequence. That's a tricky one. I want to say yes. However, there might be spots where we start a little bit different than y equaling 0. But most of the time, it will be the y-intercept, most of the time. It will change a little bit. We'll take a look at that when our transformations come into play. Okay, let's just identify real quick, yes or no, are these actually considered exponential functions? So let's start with part A. Is f of x equaling 3 to the x power considered an exponential function? So does it fit the form of what we have up here? Yeah, so what would a technically be in this first function? So in this first example, a is 1, right? So even though there doesn't look like there's an a value there, a 1 is in its spot. The base would be 3, and you have a variable as your exponent. So this is a perfect example of an exponential function. What about part B? Is part B an exponential function? No, what's wrong with it? You're right. What's wrong with it? There's an exponent. The exponent's a -4 though. There's no variable up in that exponent. So because there's no variable up there, it's not a real exponential function. It's just an exponent there, which is technically just a constant, not an exponential function. What about part C? Is part C an exponential function? Yes. Good. What about part D? Yes, now the variable is negative, but I told you that's okay. The variable can take on positive, negative fractions. As long as there's a variable in that exponent, it's okay. What about part E? Is that an exponential function? No, pi is a constant. It's not a variable. So because of that, that is not an exponential function. All right, let's actually evaluate real quickly here. So I'm going to do A, B, C, D, and then E. We'll have an open space there. All right, so evaluating, remember we're just using substitution. So technically for part A, you're doing 2 to the 4th power. In the space provided, go ahead and put what that is going to simplify to. And we'll hopefully get that for the 5 values that are given here. Now I think D and E are going to be the trickiest ones, so we may have to talk through those together. But go ahead, I'll give you some time and fill in at least A through C for sure. If you know values for A through E, or for D and E, go ahead and put them on the board. Ooh, nice job. All right, so you probably use your calculator for D and E, and that's okay. I do want to talk about algebraically how that plays out a little bit, just so we have a quick review of those fractional exponents. So 2 to the 4th is 16, 2 to the 0 is 1, anything to the 0 power is 1, by the way. We have that rule. 2 to the -3rd, that's the same thing as saying 1 over 2 to the 3rd power. So that's the same thing as 1 over 8. 1 over 8 as a decimal is your 0.125. Does anybody remember what the fractional exponent will do for 2 to the 1/2 power? What's that the same as saying? That is technically not 1 over the square root of 2, it's just the square root of 2. So how that how that works out is the 2 that's on the bottom or the denominator of the fraction is turning into the index of the square root sign or your radical. The top number, the numerator, is the exponent of what stays underneath the radical sign. So technically there is a 1 right there. There's no negative sign in part D, so there's nothing that we would technically move to the bottom of our fraction. But part E, there is. So we could go ahead and say that's 1 over 2 to the 3/2 power. And writing that out with our radical sign, that would be the square root, because your index is 2, of 2 cubed. So that's the same thing as saying 1 over the square root of 2 cubed, which is 8. So 1 over the square root of 8 is the same thing as 0.35, I believe, as a decimal. right, any questions with those? So lots of good refreshers there with those exponential or fractional exponents and how we can rearrange those algebraically. You can use a calculator though to figure those out and get the 1.41 and the 0.35 decimal answers as well. So using the calculators is totally okay. All right, so let's go ahead and actually create formulas if we're given like a sequence of patterns here. The first thing we're looking at is the starting value. So remember, we're trying to take on the form of y equals a times b to the x. And Tommy had asked, is the starting value the y-intercept? And I said, most of the time, yes. So let's go ahead and find the y-intercept for this g of x column here, because that's going to give us a starting point to creating the equation for that pattern. So what is the y-intercept of that first graph, g of x? So where are we starting? What's the initial point? Yeah, it's that y-intercept. So we have to look for the x value of 0. When x is 0, what does y equal? It equals 4. So technically 4 is going to be your starting point. B is your base. That's what you're multiplying by each time to get to the next term in your sequence. So take a look there. What are we multiplying by each time to get to the next number? Multiplying by a 3, right? And it's really easy to kind of see right up in here at the larger ones, but it is happening down lower as well. So we're multiplying by 3 each time. So 3 is going to be our base. Now we keep our exponent as just the x there, because technically we should be able to substitute in those values of -2, -1, 0, 1, and 2 into this equation now and get those corresponding y values. Let's see if we can do the same thing with h of x. So h of x, let's start with the initial value of a. What is the starting point in the h of x function? Yeah, 8 when x is 0, y is 8. What are we multiplying by this time? We're multiplying by a 1/4. So technically dividing by 4 or multiplying by 1/4 is going to give you the next term in the sequence. Good. All right, so there is your function. And this kind of leads to another question that I'm going to ask here. When I take a look at the bases, I get one as an integer value of 3 and another one as a fractional value of 1/4. How does that affect the pattern that we're given here? So if I were to keep going and extending on, how does each of those bases affect what's happening in the pattern? Yeah, so 3 makes the value increase and 1/4 makes the values decrease. So we technically have different type of exponential functions that are occurring based off of that. So the first example with the 3, if your base is greater than 1, right? If the base is greater than 1, your values increase. So I'm going to values increase here. We call this an exponential growth model because your values are getting larger over time. If your base is between 0 and 1, and notice how we are talking about positive bases here. Your base should be a positive value. your values are going to decrease over time. We call this an exponential decay model. All right, so you hopefully have heard of those terms of exponential growth and exponential decay before. Now, you're comparing it to the value of 1. So every time I look at what my base is, I can actually figure out how much it's growing or how much it's decreasing by comparing it to the value of 1, because 1 is kind of your baseline data. All right, we'll learn more about exponential growth and exponential decay in an upcoming lesson. But I just wanted to kind of point that out now to bring that back up in your memory. So when we do hit that lesson, it's not a total shock. Any questions with how we created those equations using y equals a times b to the x, and then seeing how the base actually affects the rest of the model? All right, so let's go ahead and take a look at the growth and decay functions here. So just as I had summarized on the last page, you have a lot of writing here. But in layman terms, if your value of b is larger than 1, you have a growth model. If your value of b is between 0 and 1, it's your decay. And I also said that you can figure out how fast or slow something is growing or decreasing by comparing that to the value of 1. So sometimes we will take the base and subtract 1 or add 1 to it to see what we're growing or decreasing by. So in these examples here, we would do 3 minus 1 is 2. That means that your value is basically increasing by 200% every time that you're moving on. The next one, 0.25, 1/4 is 0.25. If we subtract that from 1, you're saying that your model is decreasing by 75% each time. So if I needed an actual growth rate or decay rate for your models, you subtract your base or add to your base from 1, depending on if you're increasing or decreasing. And again, that is just your growth or decay rate. It's how fast or how slow something is increasing or decreasing by. Any questions with the exponential growth versus decay there? So again, nothing really new. We talked about the difference between growth and decay on that last slide as well. And I sneezed my headphones right off. Sorry about that, guys. All right, so the next thing we're going to talk about with your exponential decay functions, or not decay, but your exponential functions, is how do those transformations apply? Your transformations that we learned in the last couple of units here have the same effect on your exponential functions. The only difference is where your variable is located, right? The variable is located up in the exponent now. So if you are adding or subtracting something onto the variable, that's going to appear up in the exponent. So that's going to tell you whether you should be moving left or right if you have something adding or subtracting up in the exponent. If you are adding or subtracting on the outside still, like this, notice how that is not in the exponent. That has the horizontal shifting of your graph. So up or down is your rules there. You also have your stretching and your shrinking. If you're multiplying by a value out front, that is your stretches, your vertical stretches. And then the horizontal ones would be if you're multiplying the exponent by something. If you have a negative that's out on your base, or technically on your initial value, that's your reflection in the x-axis. If you have a negative in the exponent, that's your reflection in the y. So we still have the same properties that are happening with the transformations with the exponential functions. It's just that when we are affecting the x variable, it's happening up in the exponent now, because that's where the variable is located. So taking a look at part A here, what transformation is happening in this graph? So again, the parent function would be 2 to the x power. So what transformation is happening in part A? Yeah, so notice how it looks like you're subtracting 1 from the variable, which is the x. So I always told you to do opposites when it's affecting the variable itself. So that would be to the right 1, and you can see that happening in the graph below as well. The blue dashed line is the parent function of 2 to the x. The black line is after the transformation. So we're moving to the right 1. All right, let's see what's happening in part B. So notice you have a negative x. So the negative is affecting just your variable. What type of transformation is occurring there? Yeah, negatives are always a sign of a reflection. You just need to figure out, is it a reflection in the x-axis or the y? And in this case, it is the y-axis because it's affecting just the variable and not the entire equation. All right, lastly, let's see what is happening in this part C. You have 3 times 2 to the x. That is a vertical stretch because it's affecting the entire equation, and that is by a factor of 3. Good. And you can kind of see that it's getting elongated a little bit there in the black line versus the blue. Okay. So real quick with those transformation properties. So everything is still staying the same with those. It's just looking at the exponents a little bit more closely so you can figure out what type of transformation is happening there. During this unit, so besides just your exponential functions, we're also going to be looking at the function which is your natural base e. So on your calculators, you actually do have this button. You may not have noticed it, but right where it says natural log, which is your ln, above it in blue or whatever color you guys have, says e to the x power. This is your natural base of e. Technically, it has a numerical value of about 2.174 or 2.714, something like that. But your calculator does have this. You may have to graph it once in a while. So if you need to graph it, you would go to y equals. So y equals, you have to hit the second button over here, and then find where it is on the calculator. So I would technically have to hit second and then natural log, or second ln, and that's going to bring up the e. The most basic parent function is just having the exponent of the x in there. That doesn't mean that transformations can't occur to this graph. So there it is. You can see it on my screen as well. But you will want to remember that this is another representation of an exponential function. In fact, it's going to play a pretty important role when we start looking at logarithmic functions coming up. So I want to say logarithmic functions are going to start appearing in lesson 2. And the natural base of e goes hand in hand with your logarithmic functions. Any questions with the natural base e there? right now it doesn't really play too big of a role other than knowing that it's just another type of exponential function. But as we move forward, we're going to see that natural base e appear a lot, especially with our logarithmic stuff. One other thing I want to point out with your exponential functions here is there's really not any vertical asymptotes. It looks like it's going steadily up, and maybe it is kind of weaning up here, or maybe not crossing over the value of 2. It's getting close to it but doesn't cross over it. That's technically not the case and not what's happening. Remember, exponentials increase without bound. So at some point, it is going to cross over this value of x equals 2. It just might be so far off our graph we don't see it. So keep in mind with these exponential functions, there are no vertical asymptotes. There are horizontal asymptotes in that most of them do not pass over y equals 0 unless there's some type of transformation happening. Okay. The next slide here is just talking about the natural base e and how we can identify if we have a growth function or a decay function happening. And because e is the same base in every equation that you have, right? It's not changing. We have to look for a different value to identify if it's increasing or decreasing. And the value appears up in the exponent. So notice how they just rewrote it a little bit differently from our standard exponential function here. So instead of the base, we have e, but they add a k up to the exponent. And that k is going to help you identify whether the function you're looking at is a growth model or whether the function is a decay model. And it's just what you would think. It follows the same guidelines as what your base had. So if k is greater than 1, it's a growth model. And if k, well, technically I take that back. If k is positive, it's a growth model. And if k is negative, it's a decay model. So slightly different rules for the value of k there, but it's easier to kind of remember because it's exactly what we would think. If k is positive, it increases. If k is negative, it's decreasing. All right, I think I have, yep, the transformation. So let's identify the transformations that are occurring with the natural base e here. So if I have e times 2 to the x, what type of transformation do you think is happening here? So notice the 2 is being applied to just the variable of the equation. Ooh, close. It is horizontal, but it's actually not a stretch. So when we have horizontal, this is kind of the wonky one of the group, or the wacky one. So horizontal, for sure, because it's affecting just the variable, but it is a horizontal shrink by a factor of 2. So technically, because you have that horizontal, it's talking about like x over c, remember? So we always have to think reciprocal of that. You could say a horizontal stretch by a factor of 1/2. So if you really want to use a stretch, you would have to use the factor of 1/2 there based on the setup. But it is definitely horizontal. What about part B? What type of transformation is happening there? Again, notice the negative sign is just up by the variable. Yep, if it's just the variable, it's a reflection because of the negative sign, but it's in the y-axis. To be in the x-axis, it would have to be out in front of the e. All right, and then part C, we do have a 3 out in front of the e. So how is that transforming our graph? Yeah, there's your vertical stretch. Vertical stretch by 3. Now, what if I had said, I don't know, they must really favor 3 or something in this lesson. What if I had made that a -3? How would that transform my graph more? So what would be the additional transformation if I made that a -3? Yeah, it's not only the vertical stretch still, but it's also reflecting it over the x-axis. So I just wanted to give you kind of a visual representation of that reflection in the x-axis versus the y that we've been dealing with here. Good. All right, the last thing to cover today, and we're right on time, is logistic growth functions. So obviously we've been talking about exponential growth functions, but sometimes that's not realistic. We can't always run into a scenario where we can increase without bound, right? So this is how kind of your logistic growth function comes into play. Your logistic growth starts with your exponential increase there, but then it tapers off. There's a limit to what your maximum value can be. So C is what we kind of call that maximum value. So essentially what we're doing is we're introducing another horizontal asymptote. So we start with the horizontal asymptote of y being greater than or equal to 0, or y equaling 0. And then we also introduce a maximum limit. The maximum limit is going to be the C that you have in your numerator. You can see that down here because this is your basic logistic function. So it doesn't go below y equaling 0. It gets really close to that but doesn't go below it. And it will not go above y equals 1 either, because 1 is the maximum amount that it can take on. Now note that the scale right here on the y-axis goes from -0.5 to 1.5. So on this graph right here, they're counting by halves. So it is showing that it gets close to 1 for that horizontal asymptote over here. All right, you should be able to identify your logistic growth functions quite easily because you'll have kind of this extra information in the denominator. Essentially you have a fraction going on. And then you'll usually have a larger number than 1 in your numerator. So let's take a look at some examples here of these logistic growth functions. It says graph the function, which we can do in using our graphing calculator or GeoGebra. Then we want to find the y-intercepts and the horizontal asymptotes as well. All right, so let's start with the y-intercept. Let's talk about how to find the y-intercept algebraically first. So how would I find the y-intercept of a graph algebraically? You substitute 0 in for x. The same thing is applying here as well, so nothing new with that. So let's go ahead and plug 0 in for x and simplify. All right, order of operations comes into play. We need to do 0.7 to the 0 power. What is 0.7 to the 0 power? Just a 1. So technically, that gives you an 8 over 1 plus 3 times 1, which is just a 3. And then 1 plus 3 is 4. 8 divided by 4 is 2. All right, so the y-intercept is going to be 0. When x is 0, y is 2. So we can see that on the graph quite easily as well. It's important to look at the scale that they're counting by on the grid here. So why is my pointer tool working? Here we go. Notice that the first set is always your x's, and the second set is always your y's. So on the x-axis, they're counting by looks like 5s. And on the y-axis, they're counting by 2s. So if you're looking at graphs like I have here, it's important to kind of note the window they're viewing it in. All right, next we have to identify the asymptotes. So with your logistic growth functions, we know that it's going to have an asymptote of y equaling 0. What's the other asymptote that it has? What's the maximum that it's reaching? 8. Yeah, you should be able to identify these without looking at the graph. The y equals 0 is just the baseline asymptote that you have for a logistic growth function. The numerator tells you that top value. So 0 is going to be the bottom value, and the numerator tells you the top value. All right, how about part B? Let's start with the y-intercept there. And again, we'll do it algebraically first, and then graphically second. So let's find the y-intercept in part B. All right, it looks a little intimidating, right, because you have the e in there, but really e is just another form of an exponential function that's occurring. -3 times 0 is 0, so you have e to the 0 power. What is e to the 0 power? Just a 1, right? Anything to the 0 power is 1, so 2 times 1 is your 2. Then you're left with some addition, and then lastly division here. We can leave that as a 20 over 3, or we can try to reduce that or change that to a proper fraction. That'd be 6 2/3, right? Or 6.6 repeating. Okay. I think it's okay to actually leave it as your improper fraction at this point. So we'll say 0 and 20/3. But notice that 20/3 is the same as 6 2/3 or 6.6 repeating. Without looking at the graph, what are your two horizontal asymptotes? Zero and 20. Everybody agree with 0 and 20? Yep. 0 because that is the lowest you can go with your logistic growth. It doesn't make sense, especially in a story problem, to get less than 0. And then the growth factor or the growth limit there is your 20 from the numerator. Right, so logistic growth functions are not that bad, especially if we have the graph to kind of look at and compare things to. Questions with your logistic growth functions? We have one more that we can maybe squeeze in here, but any questions with these first? All right, so example 8 here, it has a logistic growth model for us that represents the population of Dallas T years after 1900. According to this model, when was the population 1 million? All right, so we don't have the skills necessarily needed yet to solve this algebraically. You might if you remember all of the rules from Algebra 2, but I feel fairly confident and certain that most of you probably don't remember all the skills needed to solve for t in this equation. So what's another route we can use? Right? Those tiny wisps will definitely bring those back up and add to them in this unit. That's the goal there. But because we don't have or don't remember all the steps to do that, what's another way we could go about answering this question? There's still another way we can go about it. You can graph it. So when in doubt, always graph it. So the first thing you're going to do is plug this monster in. So you would say y equals, and you'd have all of that. When you plug that in though, we want to make sure that we're using parentheses. So we're going to not only put parentheses. Yes, we can. It sounds like an infomercial almost. Like, can you graph it? Yes, you can. All right. Also put parentheses around the denominator here too. When you put in E, it's automatically going to give you the parentheses for the exponent there. Make sure that you're putting in this value. And we're going to change T to an X because your graph right now, or whatever device you're graphing in, it only recognizes the X and Y variables. So because they changed the variables for the different scenario that the problem is set up with, we're just going to switch it back to X and Y. We just got to know that X is representing the number of years. All right, so there's the first one. The second equation, what's going to be the second equation I graph into my coordinate plane? So the first one was easy. It gave it to us there. What's the second thing we're going to graph? And let's take a look at the question at hand. According to this model, when was the population 1 million? Yeah, y equals 1 million. This is actually going to just be a horizontal line. Yep, going through the term 1 million. Obviously, these are very large numbers. You would have to scroll out significantly to see the million mark on your y-axis. So you're going to have to trust me when I tell you that the intersection is happening at the point of x being 84.51 and y being 1 million. You can also use the intersection tool in GeoGebra and just kind of select the two lines and hope that the intersection is thrown into that column on the left for you without you having to scroll out all the way. So 84.51 is representing the number of years after 1900. So I would say by 1985, the population was over 1 million. So it technically is about halfway through the year of 1984 when the population reached 1 million. What is the cap according to this logistic growth model for the population in Texas, or the population of Dallas? How many people do they say can fit in the city of Dallas? About 1.3 million, right? So they're saying that the maximum capacity in the city is that 1,300,000 and some odd people. Good. All right, that was kind of a lot to take in. Any questions with what we covered here today? So a lot of beginning things with our exponential models here. So we got a glimpse into growth and decay. We got a refresher on what it means to be an exponential model. And then we looked at our logistic growth models as well. As we venture forth, we're going to take a look at those logarithmic equations and see how we can transform between exponential and logarithmic and all that good stuff that we probably forgot from Algebra 2. All right, I will let you go though because we have ran out of class time today. I will see you guys all again Thursday to look at 3.02. So have a great day, everyone. Bye.